Welcome. In this video we will take a look at series. And so series, these are just the sums of the terms in a sequence. So we know what sequences are. Again, we've seen those as just infinite lists of numbers with a discernible pattern. With a series, though, we're actually going to be adding the numbers together. So in a sequence, we would see just a list of numbers such as, excuse me, 1, 1/2, 1/3, 1/4, or something like that. With a series, though, we are no longer just listing the numbers out, now we're adding them together. So in a series, we'd be taking 1 plus 1/2, plus 1/3, plus 1/4, and so on and so on. So again, a sequence is just a list of numbers. We just write the numbers out separated by commas. But with a series, we're actually adding the numbers together. So series are usually denoted using what's called sigma notation, or this is also referred to as summation notation. But it's referred to as sigma notation because what we do is we use the capital Greek letter sigma. That's this symbol here. It kind of looks like a strangely shaped E. But it's the Greek letter sigma corresponds to our letter S, which stands for sum. And what we do here is we indicate the numbers that we'll be plugging into the actual terms. So we might see the sum from I equals 1 to n of the terms a sub I. And what this would mean is that we would find a sub 1, a sub 2, a sub 3, and so on, adding those together. And we would keep going until we get a sub n, which is the last term in the series. So that's what the notation is and what it means, but let's try some examples to see how this actually works. So suppose we were going to take the sum, let's say as I goes from 1 to 3, of 1 over 2 raised to the power of I. So I know I'm taking a sum here, that's what the sigma indicates to me. So I'm going to be adding the numbers together. But all I have to do here is to start by plugging in 1 for I. So if I do that, I would have 1 over 2 to the first power. Next, I plug in 2 for I. So in this case, I would have 1 over 2 squared. And again, I'm adding the terms together. The last number I plug in is the number that I see above the sigma. And so that number is 3, so in this case I would have 1 over 2 to the third power. So the number is, again, below and above the sigma. That tells us the first number that we plug in for I, and it tells us the last number that we plug in for I. And then we plug in all the other numbers in between. So in this case we're just plugging in 1, 2, and 3 for I in our formula, and then we add the values together. So this, of course, would end up becoming 1/2 plus 1/4 plus 1/8. And then, of course, we actually want to find the sum. In this case, we end up getting 7 over 8 as our result. So we often use the variable I when referring to the numbers here because that refers to what we call the index of summation. So when we're talking about the actual numbers that we plug in for the variable, that's referring to the index. But we don't always have to use the variable I. Very often with the sigma notation, we'll use other variables instead. So let's take a look at some other examples here. Suppose we wanted to take the sum this time as k goes from 1 to 5 of the expression 2k plus 3. Well, what this is telling me is that I would start by plugging in 1 for k, then 2, then 3, then 4, and finally 5, since the 5 is the number that I see on top of the sigma. So plugging in 1, I would have 2 times 1 plus 3. Next we would plug in 2, that would give me 2 times 2 plus 3. Then we would plug in 3, that gives me 2 times 3 plus 3. Then plug in 4, so we have 2 times 4 plus 3. And finally plug in 5, gives me 2 times 5 plus 3. So I'm just plugging in the numbers 1, 2, 3, 4, and 5 for k, and now I'm going to add all these terms together. So if we simplify here, for the first term we have 2 times 1 plus 3, so it's just 2 plus 3, which of course is 5. Next we have 2 times 2 plus 3, so 4 plus 3, which is 7. Then 2 times 3 plus 3, that'll be 6 plus 3, which is 9. Then 2 times 4 plus 3, that's 8 plus 3, or 11. And finally 2 times 5 plus 3, that's 10 plus 3, which gives us 13. And adding all of these numbers together, we should end up with 45 as our result. And so this is basically it when we're dealing with series and sigma notation. It's a lot like sequences where we're just plugging numbers in for the variable, typically starting with the number 1 like we see here. But we just want to make sure that when we find all of the terms in the series that we then actually add them together. And that's the big difference between a series and a sequence. A series, you add the numbers together, whereas with a sequence, you're simply writing a list. Another difference that we have for series, as opposed to sequences, is that with sequences, we generally start by plugging in the number 1 for the variable. But with series, we may start with a different number. As an example of what I'm talking about here, suppose we had the sum as j goes from 0 to 4 of 3j minus 1. Well, notice here that the first number that we're going to plug in for j is 0. But the top number we see is 4, so we will stop when we get to the number 4. So that means that we're going to plug in 0 for j, then 1, then 2, then 3, and then 4. And then, of course, we will add the numbers together. So let's do that. So by plugging in j equals 0, I would have 3 times 0 minus 1. Next, I plug in j equals 1, so that gives me 3 times 1 minus 1. Then we'll plug in 2, so it gives us 3 times 2 minus 1. Next, we plug in 3, so we have 3 times 3 minus 1. The last number I plug in is 4, and I know that because that's the number that I see on top of the sigma in my sigma notation. So this gives me the terms that I would have in this series. And again, I just want to simplify the results and add them together. So for the first term, we'd have 3 times 0 minus 1, so it would just be negative 1. Next, we have 3 times 1 minus 1, which becomes 2. Then we have 3 times 2 minus 1, which would be 5. Next, we have 3 times 3 minus 1, which is 8. And finally, 3 times 4 minus 1, which is 11. And adding these results together, we should get a final sum of 25. So again, we may not start with the first number being 1 that we plug in. We could start at any number. In this case, we were starting with j equals 0. And we could start with other values as well. So as another example here, let's take the sum, let's say as n goes from 3 to 7 of n squared. Well, in this case, we would have 3 squared, which would be 9, of course. And then the next number we would have would be 4 squared, which would be 16. We would have 5 squared, 6 squared, and 7 squared. And so simplifying the results here, we would have 9 plus 16 plus 25 plus 36 plus 49. And adding these together, our final result should be 135. Okay, well, in working with series, sometimes we will have what's called an infinite series. And we'll be working with these more a bit later on. But an infinite series is one where we have an infinite number of terms. So an example might be something like the sum, let's say, as n goes from 1 to infinity of just 4n. Well, what this would mean is that we would start by plugging in 1 for n, so that of course would give us 4. And we would plug in 2 for n, which of course would give us 8. And then plugging in 3 for n, we would get 12, and so on and so on. However, because the upper index of summation, as it's called, the upper number above the sigma, is infinity, it means that this series does not stop. It just keeps on going. And so we indicate that simply by putting the 3 dots at the end of the expression. but we don't write any more terms. So it just indicates that it keeps on going. And in certain situations, we'll be able to actually find the sums of these types of series. But just be aware that when you see a series like this that ends with the 3 dots, it just indicates that it keeps on going forever. We also want to be able to, when we're working with series, find the sigma notation from a given set of terms. So as an example here, suppose I said to find the sigma notation for the following series. Suppose I had the expression 1/4 plus 1/8 plus 1/12 plus 1/16 plus 1/20. So what we need to do here is to come up with an expression for the actual formula for the terms that we see. And so this is a lot like what we saw before in working with sequences and finding expressions for their terms. So what we need to recognize first here is that if I write out the terms sort of the long way, I could write this as 1/4 times 1 plus 1/4 times 2 plus 1/4 times 3 plus 1/4 times 4 plus 1/4 times 5. And so hopefully from this we can see that the pattern of the numbers is 1/4n. Or you can choose a different variable if you want. If you'd rather use j or k or something like that, that's fine, but I'll go ahead and use n as my variable here. But I'm not done yet because I need to realize that I'm taking a sum here. I'm adding the numbers together, so I need to include the sigma notation. So I would draw the sigma in front of this, and then I need to indicate what the index of summation is. So notice here that what we'd be plugging in is, first of all, n equals 1. Then we plug in n equals 2, and n equals 3, n equals 4, and finally n equals 5. And so that tells me the number above the sigma needs to be 5. And so this is what the sigma notation for this particular series would look like. So again, finding the formula 1/4n is really just like finding the formula for a sequence. We then just also need to include the sigma notation and indicate what the numbers are that we're actually plugging in the variable. In other words, just finding the index of summation. Let's try some other examples like that. So let's do the same thing for the series 5 plus 10 plus 15 plus 20 plus 25 and so on plus 200. Well, again, we'd want to find a pattern for the numbers that we actually see here. So notice that we're taking 5 times 1 plus 5 times 2 plus 5 times 3 plus 5 times 4 and so on, but this keeps going until we get to 200, which we should recognize as being 5 times 40. So thinking of the numbers as multiples of 5, the last one is 5 times 40, which indicates what our last number is that we're plugging in. And so hopefully it's not too difficult to tell that the actual pattern of the numbers is 5 times n. And when we write the sigma notation, we should be able to see that we want n to start at 1 and to stop when we plug in n equals 40. And so that gives us our index of summation, the actual numbers that we're plugging in for n. So that would be the sigma notation for that example. And let's try one more example like that. What if we want to find the sigma notation for the series 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... So again, notice the dots at the end here indicate that this series just keeps on going forever. So this would be an example of an infinite series. But also notice that when we look at the patterns of the numbers here, I'm going to rewrite the 1 at the beginning as 1/1 to help us recognize what our pattern is. Because notice that I can think of that as being 1/2 to the 0 power. And then we have 1/2 to the first, then 1/2 squared, 1/2 to the third, 1/2 to the fourth, etc. So I should be able to see that the pattern of my numbers is 1/2 to the nth power. But for the sigma notation here, notice that we have to have n start at 0, since our first number is 1/2 to the 0 power. And also, as we pointed out, it is an infinite series. We don't have to see a final term. It just keeps going forever. So above the sigma, I need to indicate infinity to denote that I am dealing with an infinite series here. have infinitely many terms. So that would be the sigma notation for this example. So again, it's a lot like working with sequences, just trying to find the pattern for the actual terms that we see, but also making sure to write the sigma notation and to indicate the numbers, the index of summation that we actually have.